Hi, welcome to this lecture. If you remember in the last lecture what we have seen the e-beam evaporation and thermal evaporation, which is part of the physical vapor deposition. Now, in this lecture what we will be looking at is the sputtering, which is the next part of the physical vapor deposition. Now, if you recall, the thermal evaporation had a limitation that if the material that we need to evaporate has a higher melting point than the source holder, right, the holder on which we keep the material, then we cannot use the material, because the holder will start melting as well. That is one. The second one is that some of the material, right, and one of the common limitation that goes in PVD is the shadowing effect one, and the how to cover the step, right, which is the step coverage. So, these are two issues generally that we face when we talk about the physical vapor deposition. But then there was another system which we called e-beam electron beam deposition. In that, the electron beam will hit the material on the crucible. Crucible is again a source holder, and the material loaded onto the crucible will melt and will evaporate. That was e-beam. Now, the third one that we will be talking today is called sputtering, alright, and the sputtering has advantage over e-beam or thermal, such that it can evaporate or it can deposit. It is not a evaporation technique. So, let me just correct myself, it is not an evaporation technique, but here we are using the mechanical way of depositing the material onto the substrate. Okay. The advantage of sputtering is almost every material that you want or any material that you want, you can deposit onto the substrate almost. Because there are some exceptions that may not be we may not be able to deposit via the physical vapor deposition. And when we talk about sputtering, there are 4 different types of sputtering. One is DC sputtering, direct current sputtering. Second is RF sputtering, radio frequency sputtering. Third one is magnetron sputtering. The effect of magnetron is to increase the rate of deposition, and finally we have reactive sputtering. So, let us see the slide and then we will go through that. So, as I told you, the sputtering techniques can be divided broadly into 4 categories: DC, RF, magnetron and reactive sputtering. The targets in this sputtering are of various type. If you again recall, in e-beam and thermal, we were using beads or wires, right, to as a source that we want to deposit. In this case, the target or the source would be disc, toroid, plates, etc., and it comes with different shapes and sizes. As an energetic ion strikes the surface of the material, there are 4 possibilities. So, what happens is, it is still we remember the chamber, right. So, in the chamber you again create a vacuum, it is a vacuum deposition, and when the vacuum is there, what happens that the energy that is provided to the target, right, will cause the atoms from the source or target to sputter, and the sputtering atoms with additional surface mobility will improve the step coverage and will also start depositing onto the substrate. But let us go one by one. So, what it says is, as an energetic ion strikes the surface of a material, there are 4 possibilities. First is, ions with low energies may simply bounce off the surface. Second, at low energy, which is less than 10 electron volt, the ion can be adsorbed to the surface, generating heat. The next one is, above 10 electron volt of energy, the ion penetrates into material many atomic layer spacing, that is ion implantation. We will talk about very quickly implantation techniques, and how we can dope a silicon with N type or P type, right. So, intrinsic silicon by doping can make it, we can make it extrinsic, but if you want to just create a PN junction, let us say, right, then how you can create this PN within a intrinsic silicon or even an extrinsic silicon, we will see. It is called a diffusion and ion implantation techniques. However, what we have seen is that between these two ranges, that is both energy transfer mechanism occurs and the substrate atoms or clusters of atoms will be ejected from the surface of the substrate with energies of 10 to 50 electron volt. So, the idea is that you can keep the energy between 10 electron volt more than that and 10 kilo electron volt, and somewhere this energy will help in creating or depositing the material. So, sputtering yield, if you want to talk about sputtering yield, sputterer yield is the ratio of number of sputter atoms to the number of incident ions. Okay, so again let me draw it. So, this is a chamber and this is the let us say substrate, right, and here we say that there is a disc, correct. Now, if the argon is used as a gas, then the number of ions incident onto the this target, right, at a high energy electron volts or a high energy and somewhere around 10 electron volts, little bit less than that because we said in the range, right. What will happen is that the atoms from this particular target will be dislodged and will start moving towards So, let me just create the eraser. So, when this happens, when this thing happens and when the ions are incident onto the source or target, the atoms will be dislodged and will move towards the substrate. And where is our substrate? Substrate is here, right, like any other PVD technique. So, when this happens, the deposition will start occurring, and you can see that what will happen, that when you have when the ions are incident onto the target, how many ions are incident corresponds to how many atoms are sputtered, right, or dislodged from the material is called something as a yield. So, sputtering yield can be defined as number of sputter atoms, right, number of atoms coming out from the target, dislodging from the target. This is our source or target, because we are targeting this material by incidenting the ions, which ions, argon, right, then to create the sputtering, that means dislodging the atoms and depositing onto the substrate. What can be our substrate? Substrate can be silicon, can be glass, right, can be any polymer, anything on which we want to deposit our material. So, number of sputter atoms divided by number of incident ions, right, how many atoms are sputtered corresponding how many ions are incident. So, sputtering yield depends on following things. Okay. The first one is the binding energy. So, sputtering yield is inversely proportional to the binding energy. It is proportional to the square root of energy and proportional to the ion and target atoms, that is S is proportional to M. Finally, it is proportional to the angle of incident, that is rate is proportional to the incident angle, and reduction deposition pressure gives a better yield. So, as much as you can reduce the pressure, the yield becomes better. Now, this graphs or plots shows the same thing. So, let us understand these plots. So, let me again use the eraser and erase this particular drawing, and then when we see these plots, what we see? We see that this y axis is sputtering yield, x axis is ion energy. So, as you increase the energy, the sputtering yield starts increasing, right. At certain point it will start reducing the sputtering yield, and finally, it starts somewhere around this point with very high energy, starts kind of dipping it down, right. So, this shows that what kind of energy we can use, which we call as a threshold energy, after which the sputtering will start, right. So, this is here we have written, or you can see threshold energy for sputtering. what does this graph shows? This graph shows that the sputtering yield is how it corresponds to the angle of incident. So, in this graph you can see that as the angle of incidence increases, the sputtering also increases, but then suddenly around pi by 2 it drops, or in fact it is what we call is a theta max, right, angle of incidence, which is a max angle at which the sputtering yield is maximum. So, you can see around between 62 and 70 degree the sputtering yield is maximum. Finally, with pressure, right, what happens? So, as you reduce the deposition pressure, the yield is higher, which you can very well see from this particular plot. Okay, got it. So, why we are not going into the physics of this sputtering is because we want to use this system to deposit a material onto the substrate and fabricate devices with our understanding about PVD or CVD. That is why I am not getting into details about what atoms, how it looks like, what is the rate, right, but to understand that there is a physical vapor deposition and then there are 3 techniques: thermal, e-beam, sputtering, and how it works, right. So, that you and we also have corresponding lab videos, right, you can, where we have recorded how the e-beam operation works, how chamber looks like, where is the QCM, quartz crystal monitor, where is the substrate holder, how the source looks like, how you can close the chamber, how the vacuum is created, primary pump, secondary pump, how the pressure are measured, right. There are 2 pressure gauges, one is Pirani gauge for the pressure close to 10 to power minus 3 torr, then there is a panning gauge that goes to minus 4 and about, let us say, about minus 7 torr, and then how the deposition occurs within the chamber. So, this for thermal we have recorded, for e-beam we have recorded, for sputtering we have recorded. So, you can see those recorded videos from the experimental laboratories as a part of this course. The what happens within is what I am trying to cover, right, but there are many more things which is related to physics, which we are not going into depth for this particular course. Okay. So, what you need to understand is that, okay, there is thermal evaporation, then there is e-beam evaporation, there is sputtering. In sputtering, the number of incident ions, if I improve the if I increase the number of incident ions, how many atoms are dislodged is called sputtering yield. And what it depends on? It depends on the energy, it depends on the angle of incidence, it depends on the pressure, right. This is what I want you to remember. Okay. Now, let us go to the next slide. So, as we have as we know that thin film deposition can be spin coating. Spin coating we will talk as a part of the photolithography section, and then in PVD what we have seen, physical transport material from source to substrate, because either by e-beam or by sputtering or by thermal. So, either by evaporation or by sputtering we are depositing a material from the source to the substrate. Example is evaporation and sputtering. No chemical reaction is involved except reactive sputtering. No byproducts are generally are there, generally processed after creating a very high vacuum, and the difficulty or limitation is the poor step coverage. Now, let us talk about chemical vapor deposition. CVD is a chemical process used to produce high purity, high performance solid materials. Okay. The advantage of CVD, which is chemical vapor deposition, is the step coverage becomes excellent because the reaction occurs across the substrate. So, what does it mean? Let us say you have a substrate like this, okay, substrate, and then you have deposited material and then you have patterned it. So, it looks like this. Okay. This is your material which is patterned. Now, I want to deposit another material onto this pattern, alright, such that it should also get deposited in this area as well. Alright. So, if I use chemical vapor deposition, then the reaction occurs across this particular step, right, everywhere, because the gas is everywhere. So, what happens during this one, this tap here, this angle here, this tap, right, is uniformly deposited. So, the coverage is getting better in terms of chemical, and you can see in terms of the thermal oxidation or e-beam evaporation, thermal evaporation or e-beam evaporation or even sputtering, the step coverage is poor. From this figure you can see See, it is not really covering the oxide properly, but if you go for CVD, this will not be there. So, good step coverage, good film quality is used to deposit silicon and dielectrics. The only limitation you can say, or you need to be careful, is that there are byproducts, okay, because when there is chemical reaction, the byproducts are there. So, this is the difference. Now, let us understand spin coating. Okay. So, spin coating is a procedure to deposit a thin film uniformly on a flat surface. Okay. So, you have this substrate, let us say, and if I, let us say you want to spin coat a photoresist. If I want to spin coat the photoresist onto this particular substrate, what is the procedure? The procedure is that I will first drop this one photoresist onto the substrate, like something like this, right, and then I will spin it, whole thing, okay, whole substrate I will spin it at a high RPM. What is RPM? Rotations per minute. So, as soon as I start spinning this substrate, what will happen? The photoresist on the substrate will also starts spinning, and you can see from this this image, right, you can spin in one of the directions, either clockwise or anti-clockwise, and finally, when you do that, the uniformity becomes better. Okay. So, this is how the spin coating works. When you spin the substrate, now if you spin the substrate, the question is why it will not fly, right, because the substrate is kept on a chuck and the chuck is with a vacuum. So, the substrate is holded by a vacuum and then it is rotated. So, in a very simple terms, this is kept on a chuck like this and then there is a vacuum. Okay. So, this vacuum is created with the help of a pump. Okay. Now, if you rotate this whole is a rotating chuck, all right, and including this spindle, So, it rotates, there is a vacuum that is created and the resist will get deposited. Now, we are talking about a resist, but you can talk about any other material which is in the which you want to deposit using the spin coating. Particularly, I will show you the example of spin coating when we talk about the photolithography. Okay. But spin coating, via spin coating we can coat some of the materials. For example, you want to deposit a PZT via soul gel technique, right. PZT is a piezoelectric material and soul gel technique. We create this material, then we spin coat it on a substrate. So, the easiest method to deposit a film, because you have to just put a drop or few ml of that material and then spin coat it, right. We do not require vacuum, we do not require very high vacuum like 10 to the power minus 6 minus 7 and then we do not have to worry about a complex mechanism of heating the source or using electron beam or incidenting the ions, right. So, this is very easy way of depositing the material on a flat surface. Flat surface, because we are talking about silicon or we talk about the glass. What happens if there is not flat surface? It will not get deposited uniformly. So, now if you understand this much, what can be what are the parameters on which this deposition relies on, right. The first one is the angular speed. So, if you increase the rotation, the thickness would decrease. If you decrease the rotation, thickness would increase. Then the viscosity of the liquid is extremely viscous, very difficult to deposit. Then it depends on the concentration of the solution. Then common spin coating defects. What are these possible spin coating defects? You can see bubbles or pinholes, you can see here. Swirling and streak pattern, you can see here. Non-uniform coating, you can see this one, right. So, if I give like 1, 2, 3 and 4, then this one is 1, this is 2, this one is 3, and finally this figure shows the fourth one. So, chuck mark, you can see the chuck marks are there. Chuck is so chuck is used to hold the wafer or a substrate. So, these are some of the spin coating defects. Now, let us understand what are the limitations of spin coating. See, defects are different than limitations. Okay, the limitations are low throughput, because one substrate you can load at one time, and second one is control over the deposition process and layer thickness is very poor, because just by spin coating we need to make sure that the thickness comes uniformly from substrate to substrate over large quantity, which is very difficult to really control. What I mean by is that if you coat the same material at same RPM for on different or 100 substrates, what is the accuracy of the deposition that you find it out. So, in this case it will be extremely poor. Uniformity of the deposit film is very poor compared to other techniques. Compared to, now when I say poor is not like really bad, but when you compare to CVD or PVD, it is poor. Now, let us go to 4 basic types of chemical vapor deposition. Now, from physical vapor deposition we go to chemical vapor deposition, and just again understand from periphery what exactly are different kind of CVDs. So, when you look from that angle, right, or from the top, we can see that okay, there are 4, which one? Atomic pressure CVD, low pressure CVD, metal organic CVD, plasma enhanced CVD, right. So, the advantages are high deposition rate, simple, high throughput. Which one we are talking about? APCVD. Then the disadvantages are poor uniformity, purity is less than LPCVD. Okay. So, if you want to quickly deposit, you can go for APCVD. It is very simple and it is at a high throughput. This is generally used for thick oxide deposition, but when you want to deposit a polysilicon or dielectric layer or and dope dielectric deposition, then you go for LPCVD. LPCVD has excellent uniformity and lower but reasonable deposition rate than APCVD. Then if you want to go for metal organic CVD, the advantage of MOCVD is that it can deposit semiconductors, metals, dielectric, and is extremely flexible. But the disadvantage is extremely toxic, okay, highly toxic, very expensive source material, environment deposition costs are extremely high. It is used for low cost optical 3-4 technology, some of the metallization process, tungsten and copper, but there is one more CVD which we will talk about when we are going to fabricate, or I am going to show you an example of a fabrication, is the PECVD. Plasma enhanced CVD is used to force reaction that would not possible at low temperature. That means that this all the above CVDs, APCVD, LPCVD, MOCVD, they suffer from one or second limitation, particularly the temperature requirement is extremely high during the when the reaction occurs. But in plasma enhanced CVD, the temperature can be as low as 100 degrees centigrade, and there are a lot of advantages of low temperature chemical vapor deposition, and we will take an example and I will show it to you why PECVD is preferred for certain fabrication techniques than other CVDs. The disadvantage of plasma damage is typical results. Typically that kind of results are obtained because of the damage from plasma and used for dielectric coatings like silicon dioxide and silicon nitride. So, at a glance, if you want to see, right, let us take this particular schematic, and what you see is there is a quartz tube, and the quartz tube, this orange color lines that you see are nothing but a silicon wafers, okay, silicon wafers. So, generally silicon wafers how you see is like this, right, but when I stack it then it looks like this, isn't it? If you stack it in this fashion, it looks like this. So, these are silicon wafers, and in the quartz tube when you load the silicon wafers, and then you have heating coils, and when you heat this particular quartz tube, initially you have to place the nitrogen. So, anything within the any oxygen present within the quartz tube will be flushed out. Okay. So, initially in presence of nitrogen you heat this particular quartz tube at a higher temperature. Generally we heat from 900 degree centigrade, anywhere between 900 degree centigrade and 1200 degree centigrade to, and most of the time we use this thing for silicon dioxide growth. Okay. This is thermal oxidation, silicon dioxide growth. Now, once you reach this temperature of your choice, then you can stop nitrogen and let the oxygen pass through the quartz tube. What happens is, when silicon reacts with oxygen, it forms silicon dioxide, right, as simple as that. Of course, we have a dry oxidation and wet oxidation, but right now we are just taking an example of dry oxidation, where only oxygen, dry oxygen, right, is passed through the quartz tube at a high temperature, and there is a reaction between silicon and oxygen forming silicon dioxide. Now, this is same thing is written in this particular slide, that chemical gas sources are thermally, optically or electrically activated to react with a surface to deposit a layer, and the byproducts are pumped out from the chamber, right. In a simplified model, as you can see in this particular slide, as gas flows over the substrate film, the growth is determined by the adsorption and reaction rates. So, now you see this particular schematic. What is that? There is a substrate, and then when this gas phase reaction occurs with the substrate, there can be multiple things. One is the nucleation and island step growth, which will occur here. Second one is there is some desorption will occur. Then third one is that when the gas reaction occurs, it goes to the substrate, adsorption occurs, surface diffusion occurs, and readsorption occurs, right. So, there are many things that occurs when the reaction is there within the chamber, and this is nothing but like in a bigger chamber you see like this, right. So, when the gas main gas flow region is here, and how the reaction occurs and what can be the possible solutions. One is that the film is deposited by nucleation island growth, second one is that there is a adsorption, readsorption, then the last one is a deabsorption. So, the reality deposition rate is affected by distance from the gas inlet, specifics of the reaction, and radial variance, right. So, if I have a slide, so if I kind of have an angle, right, at which I am putting the wafer, what will happen is that the wafer, that the inlet is here, right. So, the as you go towards it, right, if you have this one and you see that the gas is like this, over a period of time the concentration of the gas here will be lesser than the concentration of gas here as it passes through, is not it. So, if I tilt it, if I tilt the entire substrate holder like this, then what will happen is the reaction, even the concentration of gas decreases, the reaction rate will not decrease significantly. So, that is why we can this radial variance is important factor when we talk about the CVD. The last thing is the tricks to improve. So, when I say that okay, let us tilt the substrate, that is what I meant, that when you tilt the substrate, the rate of deposition or uniformity also improves, not really rate of deposition but more like uniformity. So, that all the substrate within the CVD will be uniformly coated. Okay. So, one is you tilt the substrate in the flow like I have just drawn, right, increase temperature along the substrate, and single wafer processing. If single wafer is there, no issue, but multiple wafers are there, then you need to make sure that all the wafers are uniformly coated with the material of our choice. But when we talk about why CVD is not so common in the laboratories, right, it requires a specific way of treating the hazard, which is a byproduct. So, even for the lab that we have recorded this thermal evaporation, E-beam or sputter, we do not keep CVD, but we have CVD as a as one of the deposition techniques in the central facility of our institute. So, the advantage are many, but then limitations or the way to handle the gases are extremely important. So, that is the main reason that the safety is an issue when we talk about CVD in common labs. Okay. However, it is an extremely important deposition technique. So, many gases used in CVD systems are toxic, when you say toxic, they are hazardous to humans, then it is corrosive in nature, then particular causes corrosion to stainless steel and other metals. It is flammable, that means when burns when exposed to ignition source and oxygen source, explosive and or pyrophoric. So, spontaneous burn or explode in air, moisture or when exposed to oxygen. So, what are the gases generally used in CVD? So, the gases are listed here, right, from ammonia, silane, arsine, phosphine, hydrogen, nitrogen oxide, hydrogen chloride, diborane, dichlorosilane. What are the hazard levels? So, it is from toxic to corrosive to flammable to oxidizer to corrosive and toxic both, right, or combinations of this. The limits also are given, the exposure time is also given, because if you are exposing more than this, like parts per million, more than 25 parts per million of ammonia if you expose, it is hazardous to health. 0.5 of silane, 0.05 of arsine, you can see the how low we are talking about, and this parts per million. So, it goes to almost parts per billion when you talk about 0.05, 0.01. 5, right, and then flammable limits also you see, it is pyrophoric. So, it is spontaneous burn, right. So, you have to be very careful when handling this kind of gases. So, that is a limitation of why we generally do not go for the chemical vapor deposition techniques generally in the common lab, but we definitely use this thing, and I will show it to you how physical deposition techniques and CVD are used to fabricate these devices. So, this is the last slide for our lecture. In the next lecture, what we will look into is how the microsensors, how to make these microsensor implants, and starting with the photolithography. Okay. So, this will be the next lecture for our course. Till then, you take care. I will see you in the next class. Bye for now.